Thank you. So thank you everyone for joining. I will talk about a work that is called Fully Secure Attribute-Based Encryption for t-CNF from LWE. All right, so let me start with what attribute-based encryption is. So we consider a public key encryption system. Normally in standard public key encryption, so there is a public key with which you can encrypt a message. And then there is a secret key, and only the person that holds the secret key can decrypt ciphertext. And normally in public key encryption, whenever you have the secret key, you can decrypt any ciphertext. In attribute-based encryption, we consider a setting that is a little bit more advanced. And what we would like to have is that we can support multiple users and potentially give them different permissions to decrypt ciphertext. So the way that it is modeled is as follows. So we assume an authority. So the authority has a master secret key, and the master secret key has the capability to decrypt any cipher system. And in addition, it is possible to take this master secret key and then to delegate permissions and generate what we call constraint keys. So now the question is how we formalize the permissions of each key, or how we determine for each ciphertext which keys are allowed to decrypt it. So there are two dual notions, and here I will consider the ciphertext policy notion. So here is how it is defined. So every secret key is associated with some unique identity, which is called the attribute of the key. So it can be any number in some large space. And then every time we want to encrypt the message, then we specify some function f, which we call the policy, and this f should specify which attributes are allowed to decrypt the message. So this function f, it takes an attribute and it outputs either 0 or 1, which determines whether a key respective to this attribute should be able to decrypt the ciphertext. So now assume that we have an attribute-based encryption system, then we can measure its quality or its expressiveness according to a few different properties. And in this talk, I will focus on two main properties. So the first one will be the kind of security guarantee that we get. So we have either a full security or selective security, and in the next few slides, I will explain in more detail what are the differences between those two notions. And in addition, the other important property is the class of supported policies that we can have in the system. So we want this to be as expressive as possible, so we can have complex access policies. Now, another thing I want to mention is that it is mostly interesting to consider the case where the attribute space is exponentially large, because if we have a small number of possible attributes, then it's actually impossible to have attribute-based encryption from any standard public encryption simply by using combinatorial techniques of multiple instances of public key encryption. So we always assume that the attribute space is of size 2 to the n. Okay, and another important definition that we have for this talk is identity-based encryption. So actually, identity-based encryption was defined before attribute-based encryption, but in this talk, I want to think of it as a special case of APE. So in identity-based encryption, still there are multiple keys in the system, but now whenever we encrypt the message, we need to specify the specific key that should be allowed to decrypt it. So it's like attribute-based encryption, but where we only support access policies that are just that only accept a single attribute. Okay, so now let me explain in more detail what are the differences between selective security and full security. Okay, so I know that intuitively the security notion that we want to have is that if a user has a secret key for some attribute X, then he is only allowed to decrypt ciphertext for policies that support these attributes. So now let's try to formalize this. So the first approach would be to look at the entire attribute space. And now for a given policy F, we can divide this attribute space to two different types of attributes. So I use the gray color to denote attributes that are authorized, and the white color to denote attributes that are not authorized to decrypt the ciphertext. And now for this specific F, we want to say that if an adversary only has keys that are not allowed to decrypt the ciphertext, then you shouldn't learn anything about the message. So assume an adversary that can have multiple different secret keys. We only limit the adversary in the way that it can only have keys for the white area, for the non-authorized area. And I didn't write it on the slide, but it should only have polynomially many keys. And then the guarantee that we would like to have is that if he only has this kind of set of keys, then it should be hard for him to decrypt the ciphertext. So the way to say this a little bit more formally is by using a security game between the challenger, which has the full decryption permissions, and the adversary. So the adversary gets to see the public key of the scheme, and then you can query for decryption keys. So in that phase, you can make multiple queries, and in each such query, he will send an attribute X, and then the challenger should generate the respective key for this attribute X and return it to the adversary. And then at some point, there will be the challenge phase where the adversary sends a policy F, and then the challenger should generate a ciphertext respective to this F. So she should encrypt either 0 or 1, and the goal of the adversary is to distinguish between those two cases. Now, the adversary can make additional key queries after the challenge phase, but just didn't write it on the slide to save space. But in case it bothers you, then you can do that. Okay, so before going into further details, I want to try to convince you why it should be hard to achieve this kind of security, to have any scheme that can be proved secure under this definition. So we want to have computational security based on some computationally hard problem. So we need to show a reduction. We show reduction that takes an adversary that can win in this security game and use it in order to solve a computationally hard problem. So we need to show.
Rotem,
yes.
Actually, there are some questions about the definitions in the window. So if you think that they're relevant, then you might want to address them before going into the reduction.
Oh yeah, thank you. Do we assume that f of x equals 0 for all queried x? Yes, so we restrict the adversary to only query for keys for attributes that are non-authorized by the policy, because otherwise he's allowed to decrypt honestly. Was the relationship between f and the ciphertext for f defined? So in the previous slide, in the definition slide, I wrote here that during encryption, you should provide an encryption algorithm with the policy F, and then the ciphertext is generated with respect to that policy. Does the encoding of the adversary's F have to be efficient? So that would be a property of the scheme, but because we want everything to run in polynomial time, and the encryption algorithm takes F, then the description should be efficient. Yeah, if I get the question correctly. Okay. Okay, so let's go back to why it should be hard to get this kind of security. So we would like to show a reduction from the adversary that has some advantage in this game into an algorithm that can solve a computationally hard problem. So in more detail, we need to construct some simulator that takes as input an instance of the computationally hard problem. And now we have to interact with the adversary in order to use his power. So in more detail, let's see what is the exact information that we have to provide to the adversary. So first we need to give him the public key. Then we should be able to answer all of the key queries. So whenever an adversary asks for a key for some X that is in the non-authorized space, the white space, then we should be able to simulate a proper key for that attribute. And eventually in the challenge phase, we have to simulate the ciphertext. So we get F, and then we need to provide the adversary with the challenge ciphertext. And the thing that should be hard for the adversary in the game is to distinguish whether this is an encryption of 0 or 1. So we have to use the capability of the adversary to do this, to distinguish between those two cases. So it means that we need to have the property in the simulator that if it is possible to decrypt the ciphertext or to distinguish between encryption of 0 and 1, then this advantage should be translated to an advantage in solving the computationally hard problem. Okay. Okay, so we have to come up with this kind of a simulator. So let's see why it's inherently hard. Okay. So let's see what is the naive approach. We need to be able to answer any possible key query. So assume that you have a simulator that can simulate keys for all possible attributes in the system, because we don't know in advance which keys the adversary will ask for. So it will allow us to answer all of the key queries, but I claim that it cannot satisfy the third property, the third requirement of the simulator, and let's see why. So if we can simulate keys for all of the possible attributes, then in particular, we can also simulate keys for authorized attributes. And once we simulate keys for authorized attributes, then by the correctness of the scheme, we can decrypt the ciphertext locally. And then, because we have the property that decrypting the ciphertext results in solving the computationally hard problem, it means that the simulator can actually locally solve the computationally hard problem without even interacting with the adversary. Okay. I cannot see if there are questions. So, okay.
Looks like we're okay for now.
Okay. Okay, so the conclusion from this discussion is that we should somehow come up with a simulator that, on one hand, can simulate keys for all of the authorized attributes, but cannot simulate keys for any non-authorized attribute. But the inherent problem with this requirement is that we don't know what are the white attributes and what are the gray attributes up until the challenge phase, because this partitioning of the attribute space is determined according to F, and the adversary only sends F during the challenge phase. But we have to already generate keys in the key queries phase. So this is why it should be hard to prove full security or adaptive security. So the first approach, yeah. Can we guess what the challenge would be? That's a good question. So the challenge is a function. So if we use if we want to support an expressive function space, then the guessing would be we will have a lot of security loss because the space is super exponentially large. So we can guess, but we will lose a lot in the security. Okay. Good. Okay. So the first approach to overcome this problem is to simply have an easier security definition or a weaker security definition. And this is called selective security. And in this setting, we require that the adversary will announce the function f the rest of the security game happens. So the way that it is translated to the security reduction is that now we only need to come up with a simulator that also gets F as input. So it gets the computationally hard problem, but it also gets F, and then it can act according to this F, and it can generate the public key in such a way that later it is only possible to generate respective keys for the non-authorized attributes. Now, it still doesn't make the problem trivial, and it took a lot of effort to come up with AB schemes that can even be proved selectively secure. But at least it overcomes this challenge that I discussed earlier. Okay. So prior to this work, the existing constructions of AB mainly rely on two types of computationally hard problems. So the first type is bilinear groups, and the second type is computationally hard problem over bilinear groups, and the second type is computationally hard problems over lattices, and more specifically LWE. And in both of those line of works, the way that things evolved is kind of similar. So first, there were constructions for with selective security for IBE. So I remind that IBE is ABE, where we only need to support the very restrictive function space where each function only authorizes a single attribute. So first, there were constructions with selective security and only for those point functions. Later, there were constructions that achieve the full security, but still for this restrictive function space. Later, there came constructions that support a larger class of functions. So in bilinear groups, it's C1, and from LWE, it's for circuits, but they both only have selective security. And then there was a large breakthrough with the constructions from bilinear groups where they achieved a fully secure ABE for an expressive function class. But still with lattices, this question remained open. So what we do in this work is to show a fully secure ABE construction, and the function class that we support is it's not all circuits, but it's t-CNF. So by t-CNF, I mean a CNF formula where each clause only has a constant locality. So it only depends on t bits of the inputs. So for example, 3SAT is 3CNF. Question? So let me go over the outline of the technique and also of this talk. So the first step would be to get lattice-based fully secure identity-based encryption, but in a different approach than was previously done. And in fact, we will take a technique that was used in the groups world, and we will translate it to lattice techniques using the PRF. The second step would be to generalize this idea, and instead of supporting only IBE, now we will support more functions, so it would be ABE. But instead of using a standard PRF, we'll use something that is called the Constraint PRF, which I will describe later what it is. And eventually, since for the second step to work, we need the Constraint PRF to satisfy some special properties, then the last step would be to actually construct a Constraint PRF that has these special properties. And this is the step where we get stuck and we can only support the t-CNF formulas instead of all circuits. Okay. Question. Is selective and full IBE known from non-bilinear assumptions? Yes, there are constructions from LWE. Or you mean from group assumptions that are non-bilinear? Yes, so there is a construction from DDH for IB, but for AB, not that I know of. Okay. Good. Okay. All right, so let me now start diving into the technical details. So the starting point of the fully secure IB from the PRF will be based on a technique by Gentry that achieved the fully secure IB for groups. So just to make sure we're on the same page, so we now consider IB. So it means that the ciphertexts are also associated with a single attribute. So I call this X prime in this slide. And then the decryption rule is that the secret key for X can decrypt the ciphertext for X prime only if they are equal. And if we use the same visualization, so now the authorized space is only a single attribute, and the non-authorized space is all of the other attributes. And again, the adversary can query for polynomially many keys in the white area, and eventually he sends this X prime and gets the challenge ciphertext respective to this X prime. Okay, so let's see how. What's the idea of Gentry? So he defined something that is called tagging, and here is how it works. So instead of using the standard attribute space, we now use a slightly larger attribute space. So we use something of quadratic size, and now we can think of it as a two-dimensional space. So each row now corresponds to an attribute of the scheme that we eventually want to achieve. But in addition, now we have this additional space that we call the tag. So now every time we want to consider an attribute, we can actually look at an attribute X and then additionally a tag T. Okay, so why is this useful? So assume now that we want to encrypt a ciphertext for some attribute X. So we first go to the row of this X, and then we randomly choose one of the columns, and we generate the ciphertext according to the resulting attribute. So the attribute now will be the actual X for which you want to encrypt, and then additionally a random tag, which corresponds to a random column. Now, when we want to generate a decryption key, so the decryption keys are associated with attributes, so we need to generate something that is allowed to decrypt the entire row, because we don't know on which tag the ciphertext is going to be. So we do something that is almost like this. So when we want to generate a secret key for some X, we will generate the key that can decrypt the entire row, except of some random tag that will be like a punctured point of this secret key. So again, we randomly choose another tag independently, and then we generate a key that can decrypt the entire row except of this specific one. Now, of course, there are efficiency issues that I don't discuss right now because the tag space is also exponential size. But assume for now that that we can do this somehow efficiently. Okay, so now in terms of correctness, this should work. Let's see if there is a question. Encryption of a random cell in the tag space means T is called. Okay, the question got deleted. Okay. Okay, I assume it's not relevant anymore.
Rotem, just to make sure that I understand this matrix. So the rows here are X's, yes, attributes?
Those X's are the attributes, yes.
The rows and the columns. The rows are the X's and the columns are the X's? SKs?
The okay, the entire matrix is the attribute space, which is equivalent to the single column that we saw in previous slides, the visualization in the previous slide.
Table form. So an entry corresponds to ciphertext, right?
An entry in this table corresponds to an attribute. I want to start from an ABE scheme that is selectively secure. So this quadratic space would be the attribute space of the selectively secure scheme. And I want to construct a scheme that is adaptively secure. And in the adaptively secure scheme, the attribute space will be only rows. So in my new construction that I now want to describe, each attribute will correspond to a single row. But in fact, I have a little bit more control than that because I use a selectively secure scheme in which I have more attributes than you can see as a user of my scheme. Does it make sense? Okay, maybe it will be clearer in a moment. So, so assume that I have this quadratic space of some underlying scheme, and now I want to encrypt respective to some x in my new scheme that I'm now constructing. So I will go to the row of the specific x, and then I will randomly select one column, and then I will generate the ciphertext respective to the attribute that corresponds to this cell in the underlying scheme that I'm using.
So Rotem, can I chime in with a couple of questions that came up? So first of all, so there was a question about if you can clarify what is the tag space, like what is the space of possible tags? And the other question is, so you're talking about the Fs and the Xs, and could you clarify what happens with the message that is being encrypted?
Okay, so the tag space will be of exponential size. That's the question. Just be I just enlarge the attribute space that I'm using in the underlying scheme. So I add additional bits to the attributes, and then I call the suffix part the tag of the attribute. And the other question was what happens with the message when I encrypt. So when I want to encrypt respective to some attribute X, then I would still encrypt the same message, but now I only change the attribute respective to which I encrypt. Because if you recall, then in the definition of IBE, whenever I want to encrypt a message, then I provide the encryption algorithm both with the message and the attribute respective to which I want to encrypt. So the message stays the same, but now the attribute would be the real attribute that I want, but in addition, some bits that describe the random tag. Okay.
I hope this answers the attendees' questions. Thanks.
I hope as well. Okay, so in terms of correctness, this abstract construction should work because the key should be able to decrypt all of the columns in the row except of one tag. And this tag is chosen randomly. And also the column under which I encrypt the ciphertext is also chosen randomly. So the only case where the decryption would fail is if the ciphertext by accident falls on the tag of the secret key. But because the tag space is very large, then this should only happen with a negligible probability. So in terms of correctness, we should be good. But now the question is, why does this help us to get adaptive security? So let's see. So again, we want to show a question. So basically, we can think of attribute space X goes to new attribute space X cross X x to x and t. So the question was if we can think of the construction, some abstraction where we get an attribute x and we map it to another attribute space. So yes, okay. Okay, so let's see why it should have to achieve the adaptive security. So here is the idea. We assume that the underlying scheme has selective security, and recall that in selective security we need to announce in advance the partitioning of the attribute space, or which attributes are the authorized attributes and which attributes should be the ones under which it is easy to decrypt the ciphertext. I hear noises. Okay. So so let's see why this is useful. So consider now that before the game begins, we commit to some partitioning of the attribute space as follows. So for each row, we will randomly select a column in advance. So instead of doing this during the encryption and during the key generation, then we will do this at the beginning of the simulation. So we'll choose a random mapping. It will be pseudo-random, but for now, assume that it's random. So for each row, we choose a random column. And now the simulator would work as follows. So every time we're asked to generate a ciphertext, then instead of choosing a random column, we will use the column that we already chose when the simulation began. And similarly, every time we're asked to generate a secret key, then instead of choosing a random cell in which it will be punctured, then we will also puncture it on the random column that we already chose at the beginning of the simulation. So what happens now in this setting is that for every given attribute, or equivalently for every row, we can both simulate a ciphertext and simulate a secret key. Because every time we're asked to simulate a secret key, we only need to simulate keys for all of the attributes except of the punctured point. And every time we are asked to simulate a ciphertext, we only need to simulate it on a single column, so we can do it on the punctured column that we already selected. And the thing to notice here is that now we don't choose the mapping randomly. I mean, we choose it randomly, but it's correlated for the secret keys and the ciphertext because we use the same points both for the keys and the ciphertext. But the adversary is not allowed to ask a ciphertext and a secret key for the same point, because once he asked a ciphertext for some attribute, then he is not allowed to query for the secret key that is allowed to decrypt this attribute. So the adversary cannot notice that we a priori choose all of the columns, and that we use the same punctured points both for the secret keys and the ciphertext. Okay. Question? Why do we need so many columns? Okay, so we want to.
This is related to the previous question about the space of tags, right? The columns, the space of columns is exactly the space of tags, right?
Yes. Why do we need so many tags? So we want the decryption failure probability to be negligible. Because if we choose the punctured point of the secret key randomly, and if it by accident falls on the same point where the ciphertext was generated, then the decryption failed. We want this to be negligible. Okay. So now the question is how to actually implement this abstract idea. Up until now, all what I said is appears in the tagging work of Gentry. So the new thing in our work is that we show how to actually implement this idea using tagging techniques, and by implementing this puncturing with a pseudorandom function. So previously in the bilinear world, the description of the punctured point was done with the random polynomial, and then there was some bound on the number of allowed queries. But now we can actually implement it with PRF, and then we can support any unbounded polynomial number of queries. So for now, I would not show the technical construction from Lattices, but this is the high-level idea.
Oh, Rotem.
Yes.
So this is a secret key method, right?
Sorry?
This is a secret key method? Or public key?
A secret key what?
Encryption. At the end, you're going to have a public key or secret key encryption?
No, it's a public key encryption. It's a public key encryption. If I assume that the underlying selectively secure scheme is public key, then are you concerned about the tags being revealed?
No. I'm just curious. You're saying your instantiation is based on a PRF.
Yes, but the PRF only appears in the security proof. It does not appear in the construction itself. So in the real construction, the tags are truly random. And in the security proof, I abuse the fact that the adversary is not allowed to ask for a ciphertext and a key for the same row, and therefore I can use PRF.
Perfect. Thank you.
Okay. Okay, so now let's see how to go from IB to AB, which means to have ciphertext that are targeted to some policy instead for single attributes. Looking again on the previous slide, let's see what the things that should be changed. So here, every ciphertext in the IB, every ciphertext was targeted for a single attribute, which is translated to a single row. But now we want to have ABE. So we want every ciphertext to be associated with some function. And then for correctness, the decryption mechanism that we want is that as long as the secret key is on any of the gray rows, then it should be possible to decrypt the ciphertext. So again, if we ignore just for this moment efficiency issues, there is a trivial way to go from IBE to ABE, which is to simply generate multiple ciphertexts. So assume that for every authorized attribute, we generate a fresh ciphertext the same way we did in the IBE. So the encryption algorithm gets as input this function f, and then he goes over all of the attributes, checks whether each attribute is authorized, and if it is authorized, then he performs the previous encryption, which is choosing a random tag and then generating the ciphertext respective to this tag. So again, this is not efficient, but if we use this approach, then we can apply exactly the same security reduction idea. So again, we will use a random mapping only in the simulation. We can use a PRF. And then whenever a secret key, there is a query for a secret key, then we will puncture the secret key on the column that we already chose for the given row. And then when there is the ciphertext query, So now for all of the authorized rows, we will generate a ciphertext on the pseudorandom column that we already committed to at the beginning of the simulation. And again, like in the IBE case, we use the fact that the adversary is only allowed to query for secret keys that are not authorized to decrypt the ciphertext. So now the adversary gets to see a ciphertext on multiple rows, which corresponds to seeing the PRF evaluation on multiple inputs, right? Because we said that the punctured point is a PRF evaluation on this given row. But we know that the adversary is never allowed to ask for a secret key that can decrypt any of the authorized rows. So he would never get to see the same pseudorandom value for the same row twice, and therefore he cannot learn that this is actually a pseudorandom value and not a truly random sample tag. So of course this is not efficient, and now let's see what are the requirements that we have in order to actually apply this idea. So the first thing is that in the ciphertext we cannot actually provide all of those ciphertexts for all of the authorized points, because there can be exponentially many. So we need to somehow have a succinct description of the ciphertext, and they should look pseudo-random, because we said that before we applied the efficiency tweak, we wanted the tags to be truly random. So now we have exponentially many ciphertexts, and they should correspond to random tags. So we must use something that is pseudo-random. And then we have the following requirements. So we need that the ciphertext can be simulated on those punctured points that we committed to at the simulation. And we need to have the property that even when the adversary gets to see the punctured points on some rows, which corresponds to asking for secret keys, then even given that, still the tags of the ciphertext look pseudo-random. Question? No. Okay.
I think there was a question of why do you need it to be a pseudo-random function rather than just random values that are sampled on the fly? So where do you use the fact that it actually is a PRF and has a succinct description? I think that was the question. I hope I understood correctly.
Okay, so I provide in the ciphertext multiple ciphertexts of the underlying scheme, where each of them corresponds to a different authorized attributes and a random tag. But now the number of authorized attributes can be exponentially large. So, and I don't want my final ciphertext to be exponentially large. So I need to provide something that is succinct, but it should correspond to exponentially many ciphertexts, where each of them in particular encodes this random tag. So I need to have exponential number of values that look random. So that immediately translates to a PRF. And that way they must be pseudo-random, because I need to describe them succinctly. Okay. So we have those two requirements where on one hand, we want to have succinct description. On the other hand, this succinct description to look pseudo-random, even given access to other points, because we need to answer the secret key queries, and to provide the punctured points for the secret keys. So we actually there's no way to use a standard PRF for that, because we need we need to provide a PRF evaluation on multiple points simultaneously without giving each of them independently. So for this, we exactly have a constraint PRF. So what is a constraint PRF? It has somewhat similar flavor to attribute-based encryption. So in standard PRF, if you don't have the secret seed, then all of the PRF evaluations look pseudo-random to you. And if you have the PRF seed, then you can compute the PRF on all possible inputs. In a constraint PRF, then there is the master seed, which again can compute the PRF on all possible inputs. But then in addition, it's possible to use this master seed and to generate constraint seeds. So a constraint seed will be associated with some poly CF. And then the idea is that it is possible to compute the PRF value using a constraint seed for F, only if f of x is allowed, only if f of x accepts this input x. So that would be the PRF value using the master seed, and that would be the PRF value using the constraint seed for f, and they should be equal conditioned on f of x equals 1. And if f of x equals 0, then the value of the PRF should look random even given the constraint seed for f. So it gives you exact permissions to only compute the PRF on some inputs, while guaranteeing that the PRF security remains on all of the other inputs. So actually, in our context, we only need the constraint PRF that is secure given a single constraint keys. There is a question. If I understand correctly, unlike the IBE case, here the PRF is used even in the construction. Am I right? True. Yes, you're right. Okay. So now let's see how to use the constrained PRF in the construction. So looking back again to the high-level idea, now we want to use the constraint PRF in order to have the efficiency properties. So instead of implementing the punctured points with standard PRF, we now implement them with the constraint PRF. So we represent this space, this punctured space by a PRF seed. And then every time we want to puncture a secret key, then we use the evaluation of the PRF on the given attribute. So X would be the row, and then in order to determine the corresponding column, we compute the PRF using the secret seed. And now when we want to generate, to simulate a ciphertext, then in order to give this succinct description of the evaluation of the PRF on multiple rows, we can simply give a constrained seed for the same function f. So it exactly corresponds to learning the tags only for the rows that are authorized by f, while guaranteeing that the tags of all of the other rows are still pseudo-random. So that's what happens in the security proof. But now we need to go back to the real construction and change it in a way that it will still be indistinguishable from the simulation. So we said that in the simulation, the ciphertext is associated with a constraint seed, which corresponds to the real seed that we chose at the beginning of the simulation. So now we need in the real construction that again the ciphertext will be associated with some constraint seed. But in the real scheme, we don't have the punctured space. So what we do is we first sample a random seed, sigma prime, and then we use it to compute a constraint seed for f. So that would be sigma prime sub f. And then we use this seed in order to succinctly describe all of the pseudo-random tags of the ciphertext. So this process of first sampling a fresh random seed corresponds to the process of sampling a random tag for the ciphertext when we were in the IBE context. So we sample this random seed, and then we compute from it the constraint seed for F. And in that way, it will later be distinguishable from the simulated ciphertext. So that should solve both of our requirements, because we have the guarantee that the constrained seed allows to compute all of the tags of the authorized attributes, but does not allow to learn anything about the tags of the other attributes. And on the other hand, it is succinct by the definition of the constraint PRF. Okay, any questions on that before I continue? Okay. Okay. So now let's briefly see how to instantiate those ideas from Lattice techniques. So I will give a brief overview of the BGG plus selective ABE construction, but it corresponds to the techniques that Rotem discussed in the previous talk. But let's first see how to do public key encryption from lattices. So we have the LWE assumption, which briefly says that given a public matrix A, and then this LWE instance, which is S times A plus E, where S and E are random and E is small, then that should be indistinguishable from A and a random vector U. So the way to use that in the public key, okay, so that should be indistinguishable from a random vector U, but then it is also possible to generate A with some secret trapdoor for A. I don't use this to denote A inverse, that denotes the trapdoor for A. So then, given this trapdoor, it should be easy to distinguish between those two cases. So the way to use this in public key encryption is as follows. So the public key would be the public matrix A, and then the secret key would be the trapdoor for the matrix A. And then in order to generate a ciphertext, then the randomness of the encryption would be fresh S and E, and then the pseudo-randomness of this value will be used to encrypt the message. I omitted the message itself from the description here, but once this value looks pseudo-random, we can use it to encrypt the message. And then given the trapdoor, it should be easy to distinguish the ciphertext from uniform, and therefore learn the message. But without the trapdoor, it should be hard. So now this high-level idea is used in BGG plus 14 in order to get a selectively secure ABE. And in high level, here is how it is done. So again, the public key is some matrix A, and then the master secret key now would be would be a trapdoor for this matrix A. And now there are three additional algorithms. So they correspond to the computation of those short age matrices that Rotem discussed in the previous hour. So there would be an algorithm that takes a matrix A and some value X and outputs a matrix A sub X. Additionally, there will be an algorithm that takes the same matrix A and some function F and outputs a matrix that we denote A sub F. And why are those algorithms interesting? Because they also have this additional relation between them. So there is an evaluation algorithm that can take an LWE instance respective to the public matrix A sub X, and also a function F. And it can evaluate the function F over this LWE instance in such a way that we will get an LWE instance respective to the matrix A sub F, and also the value of the evaluation. I see that there are questions. Is this an instantiation of the generic scheme seen before? That's what I'm aiming for, but right now I'm giving an overview of the selectively secure AB that will be used later. So that's previous work. Okay. So now, given those three algorithms, then whenever we want to generate,
can I ask you a question?
Huh?
So,
yeah,
the notation where you do encoding of X and encoding of F, X
yeah.
here is the attribute, right? And
Mm-hmm.
F is the function, so is the policy, and you're using them. And you think I should think of both of them as functions, I guess, when you write A sub X.
The encoding would be different, though.
I see. So then
two different algorithms.
I understand, but your notation is.
So there's some comments that Shafi, that you're not coming across clearly enough in terms of volume.
Okay, sorry. Maybe I shouldn't ask the question. I should just type it. I guess my question is this notation A sub X.
I see like there's an overloading of notation because they use the same thing to denote different things.
But it's a different type of for the attribute and the function.
Yeah. Yes, that would be different, a different kind of metrics. But I use this in order to emphasize that there are both public keys of LWE, public keys of LWE encryption.
And let me just connect to the previous talk. A sub X is what's A1 minus X1G, A2 minus X2G.
Yeah.
AF is the same AF. That's fine, Rotem, don't worry. AF is the same AF from before. Eval F is basically right multiplication by the H sub FX matrix. But this is the plus of
like A times H sub.
Oh,
F.
that no,
right?
that I didn't define. No. A sub F I didn't define. I meant eval F is multiplying by H sub FX.
Okay.
The row below.
Let's since we have about 5 minutes until the end of the talk, let's try to let Rotem finish with what you wanted to cover, and then we can have additional discussions.
Okay. So then, given those algorithms, then when we want to generate a secret key. Okay, so one thing I did not mention is that in this context, we consider a dual notion where the ciphertext is respective to X, and then the decryption rule or the decryption policy is respective to F. But you can always use universal circuits to exchange between them. But so in this context, we assume that the ciphertext is respective to X, then we can generate a ciphertext simply as an LWE instance respective to the matrix A sub X. And then we want to generate a constraint key for the policy F. Then we provide a trapdoor for the matrix A sub F. And of course, we need to have this addition property of the encode F function that if we have the trapdoor for the A that we begin with, then we can also compute the trapdoor for this A sub F. So the ciphertext would be respective to AX. And then in order to decrypt, we use this evaluation algorithm. So this evaluation algorithm takes the ciphertext respective to the attribute X, and it evaluates F of it, and then on it, and then we get an LWE instance respective to AF plus something that denotes whether we should decrypt or not. And then using the trapdoor for A sub F, we can we can get rid of the parts that make the decryption hard. I don't want to get more details right now, but this is in high level the mechanism of the BGG plus 14 construction. Okay. So now how the selective security simulator works there. So we get an LWE instance, which corresponds to computationally hard problem that the simulator should show the reduction to. And in addition, because we're in the selective setting, then we get in advance this attribute X. So now here is the idea. We need to provide the ciphertext an LWE instance respective to A sub X. And we also know in advance what X is going to be. So instead of choosing a random matrix A as the public key, we will generate the matrix A in such a way that if we compute and code X of it for the given X that we already know, then we will end up with the matrix B that we got as the challenge. So in that way, we can provide the adversary with an LWE challenge respective to B, when it queries for an LWE challenge respective to A sub X, because that would be the same matrix. Okay, so now let's see how to use all of that in order to implement the tagging technique with the constraint PRF. So as we saw earlier, I said that when we want to encrypt the message, we need to first sample a random seed sigma prime, a PRF seed sigma prime, and then compute the constraint PRF, the constraint key for it respective to F. So for that part, this is what we do. We sample a constraint key, a constraint PRF key for the function F. And then we use the BGG plus 14 encryption. So a nice property of the BGG plus scheme is that this evaluation algorithm, it works gate by gate. So we can actually do some part of the computation and then stop there and later continue with more gates of this computation. So what we will do, we will look at the partial evaluation of the function that takes as input a master seed of a PRF and computes the constraining algorithm, the algorithm that has the policy F hardwired in it, and it takes a master seed and outputs the constrained seed. So then we generate a BGG plus 14 ciphertext respective to this function and to the supposedly result value, which is the constraint seed that we chose randomly. But the reason that it is useful is because later in the simulation, we always begin with the same seed. And then in order to simulate the ciphertext for any F that we want, all we have to do is to compute the BGG evaluation of the constraining algorithm. And we will always end up with the BGG ciphertext respective to this algorithm, which results in the corresponding constraint key for the same F. Now, in order to generate a key for some attribute X, so as in the abstract description, we first choose a random tag, and now we want to have the property that you can only decrypt if this X is authorized by the ciphertext policy, and the tag and the tag of the secret key is different than the tag of the ciphertext. So we explicitly use this function. So this function takes the constraint C that is that should appear in the ciphertext. So that's what this function would take an input, and then it evaluates the PRF constraint seed on the attribute X, and it allows you to decrypt as long as the resulting tag does not fall on the punctured point of the secret key, or in other words, as long as this evaluation does not equal the random tag that we chose. So there's a question. Okay, we'll read the questions at the end.
Rotem, let's not take questions now. Let's not take questions now,
okay.
But rather in the end address any any unanswered questions if we have time. Is that okay?
Sure. Yeah. Okay, so now when we want to prove security, so we use the selective security proof technique of BGG plus 14. But instead of announcing the attribute. So now we only need to announce this seed, this single fixed seed that we choose, which corresponds to all of the constraint, all of the punctured tags. So now we have a selective cipher, BGG plus ciphertext respective to the seed. And whenever we are queried for a challenge ciphertext for some F, all we have to do is to evaluate the constraining function, and we'll get the required ciphertext that we need to provide with the adversary. And the last thing that I want to say is that actually for this thing to work, we need the constraint PRF to have some special properties. So I said that the BGG plus evaluation is done gate by gate, and in the encryption we use the constraint algorithm, and in the key generation we use directly the PRF evaluation. So what we need from the constraint PRF is to have this very special structural property, is that those two different circuits look exactly the same if we look at them as a sequence of gates. So the first algorithm is the algorithm that takes a master seed and computes the PRF, and the second algorithm is the algorithm that takes a master seed, first computes the constraint key for some F, and then use this constraint seed to compute the PRF on some input X. So by the correctness of the constraint PRF, the output of those algorithms should always be the same, but our requirement is stronger. We require that actually the evaluation itself will be the same. And this is why we can only do that for the t-CNF, because for now we only have a constrained PRF for this function family that satisfies this strong requirement. So is there time for questions? Can I answer?
All right. First of all, thanks, Rotem.
Okay, thank you.
And let's take. You can look at the Q&A and see if you.
Thank you.
You can look at the Q&A and see if there's questions that you prefer to address in front of everybody, and if not, then you can answer. You can still address the Q&A during the break via text.
Okay. Is there a way to leave this construction to a functional encryption scheme for some family of functions? We can take that offline because I don't have an immediate answer. Another generic question, if there is time, any hope to improve efficiency, and what parts should one look at for that? So it depends on the what kind of efficiency improvements you want to have. I think the bottleneck at this point is the efficiency limitations of the BGG plus 14, because other than that, the scheme itself is pretty similar. So yeah.
All right. Thanks, Rotem. Let's all thank Rotem again. Those of us who can